Okay, great. So we can get going. It's time. So good evening, everybody. Good morning if you are elsewhere. We are very happy to start this year's OSMU lectures. And our first speaker is Professor Mordechai Milgrom. He is a professor in the Department of Particle Physics and Astrophysics at the Weizmann Institute in Rehovot, Israel. Professor Milgrom received his BSc degree from the Hebrew University of Jerusalem in 1966. Later, he studied at the Weizmann Institute of Science and completed his doctorate in 1972. And before 1980, he worked primarily on high-energy astrophysics and became well known for his kinematical model of the star system SS433. In the academic years 1980-81 and 1985-86, he was at the Institute for Advanced Study in Princeton, and in 1983 he proposed modified Newtonian dynamics, MOND, as an alternative to the dark matter and galaxy rotation curve problems. Preliminary work and discussions on this subject had started as early as 1981. I want to take a couple of minutes to quote from an article by Ralph Sanders in 2015 in the Canadian Journal of Physics. I encourage you to read this beautiful article if you have not read it already. It's called A Historical Perspective on Modified Newtonian Dynamics, and I quote, MOND is solely the invention of Mordechai Milgrom. The idea of an acceleration-based modification of dynamics or gravity would have probably occurred to someone else sooner or later, but it is safe to say that in the early 1980s, no one but Milgrom had considered such a possible modification as an alternative to astrophysical dark matter. It was a brilliant stroke of insight to realize that astronomical systems were not only characterized by large scale, but also by low internal accelerations, and that this could account for the known systematics in the kinematics and photometry of galactic systems. However, the idea was hardly greeted with overwhelming enthusiasm. And just a few more lines, he says, before 1980, Milgrom had worked primarily in high-energy astrophysics and was well known for his highly successful model of SS433. During a sabbatical year at the Princeton Institute for Advanced Study, he decided to consider the dynamics of galaxies and galaxy systems in general, and the dark matter problem in particular, taking advantage of the considerable expertise on this subject at Princeton. He felt that so long as the only evidence for dark matter on astronomical scales was its putative global gravitational or dynamical effects, its presumed existence is not independent of the assumed law of gravity or dynamics on those scales. Thus, so long as no candidate dark matter objects or particles have been identified, it was legitimate to look for alternative solutions to the discrepancy in modifications of Newtonian gravity or dynamics. Such a point of view seems hardly radical at all, but an entirely reasonable scientific approach. Quote. So with those words, Moti, we hand it over to you. It's a great pleasure to have you with us today to review MOND.
Thank you very much, Tejinder, for inviting me and for the introduction, and thank you all for attending. So as my abstract says, this is meant as a general review of MOND, intended mostly for people who do not know very much about MOND. But if there are any MOND veterans among you, I hope that you can also learn something new from this. I hope you know that as much that MOND was indeed propounded in the early 80s as a possible alternative to dark matter. I won't repeat all the evidence that has accumulated before the 80s and after the 80s for the presence of an anomaly or anomalies in the dynamical behavior of galaxies and galactic systems and the universe at large. The anomaly, just to say briefly, of course, is that the masses of these systems, as determined by studying the motion of test particles in them are much larger than the masses that we actually see directly. And the mainstream explanation for this is, of course, the invocation of the presence of large quantities of so-called dark matter, some matter, the nature of which we are still in the dark, really. But at least we know that there's no known form of matter, any that is accounted for by the standard model of particle physics, that can be the dark matter. All possible candidates of this kind have been discounted. And so it has to be something new. We don't know what it is. At any rate, be that as it may, in the early 80s, proposed an alternative, noting that all the determination, all the appearances of anomalies hinge on, basically, if we don't go beyond the non-relativistic regime at the moment, they all hinge on Newton's second law and the law of gravity. So if either of these or both had to be amended in some way in the realm of the galaxies, and of course in a way that will not destroy or make us lose all the successes of standard dynamics in the solar system and so on. If this can be done in a way that will account for the anomalies, then it could be an alternative explanation without dark matter. So jumping right in, once I started thinking in this vein, I, of course, asked myself what system parameter could be responsible for this, because as usually in the case of quantum mechanics, relativity, there's always some attribute that differ in systems that are governed by, let's say, quantum mechanics, and those that are not, those that are classical. So in the case of quantum mechanics, it's H bar, of course. In the case of relativity, it is C. What system characteristic could be responsible for such departures in the case of galactic anomalies? To make a long story short, in the end, I zeroed in on the acceleration. So the accelerations in galactic systems are many orders of magnitude. Typically, they are many orders of magnitude smaller than what one encounters in the solar system and, of course, on Earth and so on. So it's acceleration, let us say. So then you have to introduce a constant with the dimensions of acceleration. And that will play, in fact, a multiple role, but the first role is to delimit the validity regime of standard dynamics. So you'd say this was called A naught, and then you would say for accelerations much larger than A naught, such as found in the solar system and so on, you expect to restore Newtonian dynamics. Let's still remain in the non-relativistic regime. And but below, for accelerations below, much below A0, something else should happen. And exactly what is basically the crux of the whole issue. So before actually introducing more formally the basic axioms of MOND, I just go very briefly on my at least intended overview. I'm not sure I will succeed in covering everything. So the first will be this introduction, as I said. I will put a lot of emphasis on predictions of MOND and the way they face observational tests and so on. Right. One critical point to notice is indeed that this constant A naught will be shown to appear with several of its faces in many of the data in different roles, and they all have, give you the same value, of course. Otherwise, I won't be speaking here. An interesting point is that this A naught, at least the value that we determine for it from different phenomena, happens to have some cosmological connotations or some possible connection with cosmology. It's called a coincidence in quotations, because it might not be a mere coincidence. It might signify something very deep. Right, and then I just attempt to discuss some practical sort of implications of this coincidence, even if it's not of very deep meaning. The fact that it exists makes some things quite interesting. Then I'll just go probably very briefly over MOND COEs. There are quite a few that have been suggested to date. And I try to explain why there are so many COEs. How can we live with so many COEs at the same time? And then maybe philosophizing a bit on possible origins of this whole idea. Right, so the basic axiom, basic tenets of MOND are as follows. As I said, we introduce a new constant called A naught with dimensions of acceleration. So again, in the non-relativistic regime, I should say that most of the dynamics, except for cosmology and perhaps gravitational lensing, we don't really need relativistic extension. We can live with non-relativistic description of a COE. So let's for the time being stay there. So we have G and A naught as our constants in the COE. I'm not saying it could be, as I said, a modification of Newtonian gravity or Newtonian inertia. We need some correspondence principle, like in quantum mechanics, where H bar goes to 0. We are supposed to recover the classical predictions, and so it is in this case. So on system with accelerations much larger than A naught, which formally can be gotten by, if you have a COE, if you have some equation, MOND equation, you take A naught to 0, which makes all the relevant acceleration in the system much larger than E0, you expect to recover Newtonian results. Okay, so as I said, the crux of the whole thing is what happens in the opposite limit when you're dealing with accelerations much smaller than A naught. Again, you can formally achieve this by taking in formula in a COE, you take A naught to infinity. But the thing is that at the same time, this is the correct limit to take. You have to take G, big G to 0. I suppose you can see my cursor, right? When I move it on the transparency?
Yes.
Okay, good. So as I said, the limit is A naught going to 0 to infinity. At the same time, G goes to 0 with this big A naught equals G times A naught kept fixed. We will understand better why in a minute, perhaps. And there is also small print, which is, I think, obvious, but you still have to state it, and that is that you don't want, or at least you don't expect, other dimension full constants in the COE, and also not, you don't want any dimensionless, let's say, important constants that are very small or very much larger than 1. This will enter importantly because, for example, because, so we have accelerations, I said, much larger than A naught, we expect Newton, much smaller than A naught, we expect, so I didn't say what we expect in this limit that I just described. We want the COE to become space-time scale invariant, namely, and I'll explain what it means in a minute. Anyway, it's formally invariance to multiplying all times and all lengths in the system by the same factor. Right, so you want the transition from the Newtonian regime to the MOND regime to occur within a range of order A naught around the value of A naught. You don't want to say that, okay, there's something going on around A naught, but Newtonian dynamics is recovered only at 100 times A naught, or that this scale invariance is valid only at 1/100th of A naught. No, you want to roughly, let's say at half A naught or below, it becomes already deep MOND, which is how I shall refer to this limit. And at twice A naught, it becomes roughly becomes Newtonian. Okay, so this is the small print. Right, and we can take this as the effective definition of MOND at present. Now, these are only axioms. Of course, we will have to dress them with some theory, more basic, hopefully theory based on an action and so on, with all the symmetries, with all the conservation laws, and so on. But for now, this is how I define the MOND. So any theory that satisfies these axioms, I'll take the liberty of calling a MOND theory. Okay, just a few words in explanation of what is meant by scaling invariant. Can you see that the titles of the transparencies, because they are blocked?
Yes. Yeah, this is called scale invariance.
Right. Okay, because on my screen they are blocked somehow. Anyway, what I mean is this: what does it mean to have a symmetry in nature? So one definition is, of course, that the equations of motion or the field equations are invariant under this. But you can also express it by saying that take any solution, any valid solution of your theory, apply the symmetry operation to it, and you get another valid solution. So in the present case, if you take any, let's say, some galactic system or a many-body system with all sorts of masses and consider its full time history, and this is a solution of your theory of the deep MOND. Now I'm talking about deep MOND because I'm talking about scaling invariant. Then take another system with another history, gotten from the first by just multiplying all distances by same factor and all the times stretched by the same factor, masses remain the same. So you get another valid theory. And it is easy to see that Newtonian dynamics, the combined second law plus gravity, is not scale invariant, because let's say the gravitational force scales like 1 over lambda square because of this r square factor, but acceleration is length over time square, so it scales only as 1 over lambda, so this is not scale invariant. You can make it scale invariant by either making incidentally, I should say that historically, the fact that this deep MOND satisfies scale invariance was realized later on, some years later. Initially, it was suggested as some, just as an effective new relation of this type. So you can make it scale invariance either by leaving gravity intact, Newtonian gravity is still valid, but taking the inertia to be not proportional to acceleration, but somehow proportional to the square of the acceleration. And then for dimensional reasons, there's this factor. Or you can leave the second law intact, but change Newtonian gravity in some way that effectively, again, in the deep MOND limit, far away from masses where the accelerations are very small, the force becomes proportional to 1 over the distance. And then, again, for dimensional reasons, it has to be of this form. Okay, so given this, it turns out that just given these basic axioms, you can already make quite a few very far-reaching predictions, even without having a theory. And this has a precedence, of course, in other cases where a new paradigm, a new theory is put on the table, starting usually with some basic principles. For example, in relativity, let's say general relativity, it could have been, let's say, okay, in special relativity, it could have been, let's say, the constancy of the independence of the speed of light on the observer, which already has some very important consequences. In the case of relativity, we know that the equivalence principle, Einstein's elevator thought experiment, preceded GR by quite a few years. And it already gave rise to very important predictions, such as gravitational redshift and so on. And the same in quantum mechanics, we had many predictions. Of course, black body, photoelectric effect, specific heat of solids, and of course, Bohr's atom and so on, before we had Schrödinger. And the case is very similar here, but I just want to give you the sort of the main tool for making these predictions. So as I'll say in a minute, there are predictions that relate only to the deep MOND regime. So you just rely on the assumed scaling invariance and make predictions about systems that are fully in the deep MOND regime. There are many such systems, low surface brightness galaxies, for example, dwarf galaxies, low surface brightness disk galaxies, and so on. They are fully in the deep MOND regime. Accelerations everywhere in them are much smaller than A naught. So this is one type of prediction. The other sort of type in this vein is predictions concerning the transition. So MOND also predicts a transition between the deep MOND regime and Newtonian, and this should always occur around A naught. And so A naught and some quantities that are derived from it by combining it with G, for example, let's say A0 over G is an important quantity that will enter. And so there are predictions that say something about the importance or the centrality of such quantities as transition. Okay, so this let's see what can be done just for scaling invariant. So what we consider a system of masses, say MP. This trajectory is a full history of the system. It could be a galaxy, a cluster, whatever. So first thing to realize that in any theoretical result, any prediction of any MOND theory, namely a theory that embodies the basic axioms of MOND, and in particular that has the scaling invariance in the low acceleration limit, in any such theory, in the deep MOND limit of the theory, A naught and G cannot appear separately. They must appear always in the combination big A0, G times A naught. Now, why is that? Okay, the thing is this, scaling, okay, instead of, let's say we have some result in the deep MOND regime, a claimed result. Now, it has to be scale invariant, namely it has to be, it's an equation between different measured quantities, and it has radii and the time in it and so on. Suppose you only make now a transformation of the units of time and distance and length by the same factor. Then, of course, the equation should remain the same. They cannot change dimensional consistency and so on. Now I take but of course the values of the constants change and so on, and also the values of the degrees of freedom. Now, when you make a scaling transformation, you only apply to the degrees of freedom. Of course, you don't apply to the it's not a unit transformation. You don't apply to the constants. So if you take back, now you applied back the same multiplication of all lengths and all times, but now considered as a scaling transformation. So it applies only to the degrees of freedom. All the degrees of freedom in the equation go back to the same the value they had before. So you go forth with a unit transformation and back with the scale transformation. It is scale invariant, so the equation should still remain the same. But the values of the constants are those after the application of the unit transformation. So they will be different. So the equation cannot be scale invariant unless the constants that appear in the theory are invariant to change of units of length and time by the same factor. I hope I made myself clear. Now, if you look at G and A naught separately, they don't have this property. They don't retain their value if you just change, decide to work in millimeters instead of meters and milliseconds instead of seconds. Okay, they get a different values, but not a big A0. So it is the only constant that can appear in the deep MOND regime. Okay. already an important realization. But once you realize this, it turns out that there is the deep MOND limit must in fact enjoy a rather larger, a two-family, a two parameters or a family of transformations, of invariances, and they are written here. It is simply because A naught is not just invariant to changing the units of length and time by the same factor. It's also invariant at the change of units of time, length, and mass by the following factors. So times are multiplied by factor beta. Okay, the fact that you have a t over beta here is okay because t is a dependent variable, so it works. It's the correct thing. So you multiply all times by beta, all lengths by alpha beta, and so all the velocities naturally are multiplied just by alpha. All masses are multiplied by alpha to the fourth power. This is when you work with a discrete system. When you work with continuum, then density transformed like this, V transformed like this. All equations in the deep MOND regime must be invariant under this two-parameter family. This has hugely important consequences. For example, take a family of galaxies, all having the same, how should I say, same shape of the mass distribution. Let's say all exponential disks. By exponential disk, mean the surface density is just an exponential law. It has some scale length, e to the minus r over some scale length. Now, all this, and let's take them all in the deep MOND regime, but they can have different masses and different sizes. Now, this tells you that MOND predicts that they will all have the same, basically, that you see that the mass goes like this, that the velocity, they have the same velocity curve whose amplitude and stretch behave in this way. They are all determined. If you measure the velocity of the velocity curve of one exponential disk in MOND, and you measured it for all of them, basically. Okay, and in a few slides I will list some more predictions, but essentially all those that relate specifically to the deep MOND regime follow from this set of invariances, which follow from the scale invariance, and the fact that you can only use G and A zero. Right. Okay. So predictions again. One should realize that there are, broadly speaking, there are two types of predictions that one can make from MOND, and those that I like to call primary prediction or first-tier predictions would be predictions that follow from only the basic axioms, even before you have a theory. And these predictions are so important. Why are they important? Because they are guaranteed to be made by all theories that I defined as MOND theories. All theories that embody the basic axioms should make these predictions because they follow only from the basic axioms. And there are quite a few of these. And in fact, the most easy to check predictions are of this type. And that is why basically it has taken basically essentially a long time, and we are still not there, to pinpoint on a single theory, because there have been many theories of MOND suggested theories that satisfy the axioms, but they essentially they differ very little on this basic, on these primary predictions. And once these predictions have been verified, but which is good on one hand, but then you cannot really use them to distinguish between theories. Okay, so that's one distinction. The other, as I said, I already mentioned, distinction between deep MOND predictions and the transition. Okay, so yes, I intend to speak of theories towards the end, and I'll tell you, I consider phenomenology still to be the sort of raison d'etre of MOND. We don't need MOND like we needed general relativity, or we now need theory of quantum gravity because of some deep philosophical theoretical reasons. It is simply the fact that there are these anomalies and we want to account for them. And the most important and the most convincing and cogent reason for studying MOND is the phenomenological success. And so that is what I will put emphasis on, not on theory, but just so that we all know. And there are theories here that just a brief description of two of the essentially workhorses that have been used extensively, for example, for n-body calculations in MOND and so on, because if we actually want to calculate interacting galaxies or whatever, we cannot use the basic tenets for this. We need some theory. So the first was a theory called Aqua. This was very early in the early 80s, a collaboration with Jacob Bekenstein. And what it does is generalize the Poisson equation. So it counts as a modified gravity theory. It leaves the second law intact in that there is still a gravitational potential, and the acceleration of the test particle is still minus the gradient of the potential. However, the potential is not determined from the Poisson equation, which is this. It is determined from some MOND equation. And the departure is expressed by the fact that in here, in the gradient, there is some function introduced. We call it interpolating function. It interpolates between Newtonian regime and MOND regime. And instead of the Laplacian of phi equals 4 pi g-rho, it's this gradient of mu times grad phi equals 4 pi g-rho. Now, there are many systems in physics that actually satisfy such an equation. For example, the equation for the electric medium with the electric constant that depends on field strength, and well, there are some others. Even some flow problems can be described in this way. And then, of course, this mu, the transparency doesn't say it, but you want in the limit of high accelerations, namely the argument of mu, which is just the acceleration over a naught becoming very large, you want it to go to 1 so as to restore Newtonian dynamics. In the other limit of very small argument, you want the system, the theory to become scale invariant. This requires that mu becomes linear in its argument, and then you can easily see this case like 1 over lambda cube, this like every power of the gradient of a derivative is 1 over lambda, so we will have 1, 2, 3. Good. This is one theory. Another theory which is in a similar spirit, but in fact turns out to be rather more amenable to computations because it is so-called quasi-linear. It's called QMOND. Never mind. I will not describe exactly what it is. I should only say that they are both derivable from actions. They enhance because they have the usual symmetries, translation, rotation, time translation, and so on. So they from the Noether theorem, they satisfy the standard conservation law, momentum, angular momentum energy, and so on. Also, I should just mention in passing, I will hopefully come back to this later. They have been extended to relativistic theories. And the relativistic theories that give this in the non-relativistic limit. But both of these theories give, in fact, quite similar results. I mean, people have tried to find differences, but they're really, given the uncertainties and systematics in astronomical observations, it's very hard to distinguish between them. Schematically, okay, if you strip, let's say, the gradient here, let's say in a spherical system, if there's no curl field, so if the divergence of two fields are the same, then the fields are the same. So schematically, this will give some relation between G, which is the predicted, the expected, and hopefully the measured acceleration, and the Newtonian acceleration, calculated from the distribution of masses now, not measured from dynamics, but actually just from the mass distribution. So MOND predicts, this would predict such an algebraic relation with, again, mu going to 1 for high G and going to G over A naught for low G. So, okay, G equals Gn for high G and G squared behaving like this. And as this constitute modified gravity because we modify the gravitational field, leaves the second law intact. But there is my favorite actually avenue for exploring theories, for reasons I don't have time to enter into here, is so-called modified inertia, where actually it was my initial hope. Modified inertia would be modify somehow the inertia term. Mach's principle tells us, or maybe we should think that it is so, that inertia is some maybe acquired property of bodies, is not something well inherent. So maybe if it is acquired, then why should it necessarily be just a proportional to acceleration? In fact, in special relativity, we know that it is not. Somewhat different. So in MOND, it could be yet different, but I will not enter into this. Again, I've given a talk about this in the recent conference in St. Andrews, and it's on YouTube. People can watch it. Good. So some of the predictions that are made. First of all, scale invariance immediately tells you that if you have, let's say, a particle orbiting a point mass, and now you apply the scaling, you increase the radius of the orbit by the appropriate factor lambda, and you also increase the orbital times by the same factor, so velocities remain the same. So it basically is telling you that the orbital speed is independent of orbital radius. Very much unlike Kepler's laws, of course, which says that for a point mass like the sun, velocity should go down like 1 over square root of r. Here, velocities become independent of r, just from scale invariance. So it's not even MOND. You don't even use a naught or the fact that it hinges on acceleration. Just scale invariant tells you this. So this gives rise to a prediction of asymptotically flat rotation curves, because if you look at the galaxy and look at test particles that orbit it at very large distances, then on one hand they fall in the low acceleration regime. So the scale invariance should apply according to MOND, and on the other hand, they are so far from the mass that you can think about it as a point mass. So, in principle, you have to apply the scaling also to the galaxy itself. You have to puff it up. So, if you are inside the galaxy, you cannot just say that velocities are constant, are independent of orbital radius in the MOND regime, because the galaxy itself also has to be puffed up. But if you are far outside, that doesn't do anything. You're still left with mass. So actually, I should say here in parentheses, I indicated that if you want to mimic these predictions in the realm of dark matter, in the dark matter paradigm, where you have baryons B and halo H, then you know that some of the observables that you make are characteristics of the baryons alone. Some are of the halo, and some are sort of combined. So I just try to indicate here that if you want to stick to dark matter, but you want to account for all these predictions and successes with dark matter, you need to account for all of this not in different aspects of dark matter. Some are predictions that pertain only to baryons, to the baryons. Some are predictions pertain only to the halo, and some are combined. So, for instance, the asymptotic velocity, first of all, dark matter does not predict asymptotically flat rotation curves. And it seems to be becoming an issue. In fact, with the advent, recent Stacy was involved in this of measuring rotation curves using weak lensing to very large radii, and it doesn't seem that they go down as dark matter would predict. But let us say we're still using just rotation curves as measured traditionally with massive particles, and you can, in the framework of dark matter, sort of predict that there is some range of radii in which the rotation curve is flat, fine. But the velocity of the rotation curve, this flat velocity is determined by the halo alone, because at this large radii, it's the halo that becomes dominant already. Got it. There, MOND makes another prediction, again, based on the basic tenets alone, because once you know that the velocity is constant, okay, so what does it depend on? It can only depend on the mass, the central mass, the point mass, and your constants, G and A naught, but as we said, it must be big A naught that appears, and dimensionally, it can only be this relation, the V asymptotic to the power of 4 must be proportional to M times A naught. So this is where the normalization of, so we choose the normalization of A naught such that equality, once and for all, of course, such that equality in this relation, and not just proportionality. So the normalization of A naught is determined in this way. Now, but you see, M here is the baryonic mass, of course. There's no dark matter in MOND. So if this relation is satisfied in the data, as we shall see, and we have realized for many years that it does, then you are basically saying that the baryons alone, the baryons that reside in the very center of the halo, and in fact, whose contribution to the total sort of presumed mass is very small, baryons alone determine the asymptotic speed, which is presumably determined by the halo. So maybe there is some sort of conspiracy here, requires explanation. I should say that any of these predictions, you can construct models of galaxies that satisfy, that within of halo plus baryons, that satisfy any set of these relations and not the other. So really each of these requires separated independent explanation in the framework of dark matter. So I will not dwell very much on the other predictions because I really am running much ahead of the allotted time. But anyway, I just mentioned very briefly, okay, if you have a system that is supported by pressure, by random motion, you predict a relation like this, that the velocity dispersion to the power of force should again be proportional to M times A naught. It is not the same prediction, it's a very different prediction. This holds not only asymptotically, it holds inside and so on. And this eta has to be of order 1, depending somewhat on system parameters, depending on the theory also. But you can show that it has to be of order 1. Okay, so these are predictions, all 3 of these that pertain to the deep MOND regime. Here is one that pertains to the role of A naught as a transition parameter, the limiter. And it says that in all rotation curves, the discrepancy should always appear when the value of V square over R is roughly A naught. Good. Another prediction that pertains to, and again, it is one that sort of couples baryons and halo. Another prediction is that this quantity A naught over 2 pi g, it has dimensions of of mass per unit area, namely a surface density, MOND predicts that it plays an important role, namely that galaxies with surface densities lower than this should behave differently from galaxies with higher surface densities. Again, another prediction that, okay, I will mention this when I actually show you the data later on. And essentially, the full rotation curves are really in MOND are determined just from the baryon distribution alone. Again, to within differences between theories. But you see, you know, people try different theories, and all those that have been put on the table so far give essentially very similar rotation curves. So I would call all of these what I call primary predictions, following only from the basic tenets, and there's some examples of secondary predictions. For example, as I said, details of rotation curves may differ between theories. There is something important called the external field effect, which tells us that even a system that is like a globular cluster or dwarf galaxy falling in the field of a mother galaxy, or a galaxy falling in the field of a cluster, when you look at its internal dynamics, you know, in general relativity, there's the principle, the strong principle of equivalence that tells us that when a system, when it is small enough, of course, no tidal effects and so on, is actually falling freely gravitationally, there's no way you can tell from inside the system. This is not the case here in MOND. In MOND, there's some concept of absolute acceleration that enters, and okay, so what matters is the absolute acceleration. So if a system is falling in an external field, its internal dynamics can be affected by the external field, if the external field is dominant, of course. Okay, but the details of the workings of this effect, while it is generic, I would say, to MOND because of its nonlinearity. Okay, generality is not also nonlinear, so it's the particular type of nonlinearity. It's generic, but again, different theories can differ greatly, and you can actually you can write theories in which this effect does not appear. The phenomenon of dynamical friction can differ between theories, and you cannot derive it just from the basic tenets. I said there was in the deep MOND regime there is a rather tight correlation between the mass, the baryonic mass, and velocity dispersion, but the exact coefficient can depend on theory, so it will count as a secondary prediction. And also the effects of MOND in high acceleration systems, such as the inner solar system, where the Earth is going around the sun at accelerations that are 10 to the 8 times a naught. So accelerations are very high. However, there are some because you can measure accurately in the solar system, there might be some remnant effects of MOND that can be detected, and different theories do differ, can even differ greatly on what they predict for this. Okay, so just very quickly some tests and predictions and so on. Incidentally, I just noticed that Stacy McGow, I think, is attending our Zoom meeting, if I'm not mistaken. Will be giving the next. Yeah, okay. So he will be giving the next OSMU talk, and I hope he will also speak, because it's contributed a lot to testing and verification of MOND and so on. So in fact, this is taken from, these are rotation curves taken from the, it's only part of the more than 100 galaxies that have been assembled and accumulated and tested in Stacy's group. In this case, it's taken from Lee et al. What you see here are the data, of course. measured rotation curves. You also see a rotation curve that is predicted by Newtonian dynamics just from the baryonic mass distribution. If there's more than one component that they are showed separately. And essentially the line that you don't see that is going through the data points in most cases, not always, like here, but the line that is, considering that we're dealing with astronomy, no, this is not so good, is the MOND prediction. When I say prediction, I should mention that there's some fit parameters that you can probably not see. So the distance is allowed to vary a little bit, and the inclination angle is also allowed to vary a little bit so as to get the best match. But you will see, which you probably cannot, because I see the numbers are very small. You don't need much of. So the topic of the. Who is sorry?
I think Subir, did you say something, or should you be mute? Oh, he's muted. Go ahead. Subir Sarkar is here, but
okay, I think this speaks for itself. I mean that you can with parameters that are very reasonable and in fact don't differ much from what one gets with independently of MOND, the predicted rotation curves agree very well. And you see sometimes they account for huge discrepancies. Remember the mass discrepancy, the mass goes like square of the velocity. So some of these are very large discrepancies indeed.
Sorry, I meant to say, Moti, is it not true that the fitting parameter is the mass to light ratio? And in fact, you require values that are perfectly consistent with independent measures of the mass to light ratio for these galaxies.
Right, but in fact, Stacy may be able to say more of this. In the past, when we use mass to light ratios in like let's say B or V bands, photometric bands, they vary a lot from galaxy to galaxies.
Yes.
What is special about this spark sample is that they used infrared from Spitzer. That's the S from spark from Spitzer, and the infrared, we believe, and there's quite a few substantiations for this, that mass to light ratio varies very little, in fact.
I see. Yes. Thank you.
But I know they probably fitted M over L, or they left it the same. But anyway, coming to this, these are from Bob Sanders' recent paper, very important. Why? Because he just collected from the literature rotation curves of galaxies that are first of all, very deep in the MOND regime. Okay, so we can be safe in just applying to them the deep MOND limit. Secondly, and very importantly, such galaxies are known to be dominated. The baryonic budget of them is dominated by gas, by H1 gas, for which and stars contribute only very little. So it's quite immaterial what the mass to light ratio is. Okay, so these are essentially completely parameter-free predictions of MOND. Okay, there's no free parameter. Okay, so it just took the inclinations from the literature, the distances from the literature. Mass to light ratios are unimportant. What I defined before as the interpolating function is unimportant because you are deep in the MOND regime. You're sitting in the linear regime. And so these are, I think it's very impressive, just predictions. Unescapable, absolute predictions. I cannot, overemphasize this. You see some slight differences, and in fact, Bob showed that very, very reasonably they can be accounted by slight change, slight adjustment of the distance.
Could I ask you at this stage, for comparison, what does the cold dark matter model have to do to be able to predict the rotation curve?
I don't think they can. I really did not mean at all to disparage or say anything bad about dark matter, but they can say nothing. Why? Because think about how present-day galaxies have formed in the realm of the lambda CDM. Okay, so each of present-day galaxies has undergone, a very violent history of mergers. Okay, collisions, ejection. I haven't mentioned this, but the ratio of baryons to dark matter in galaxies today is much smaller, maybe 50 times smaller or tens of times smaller than the cosmic value of about 1 to 5. Very few people realize this. That, okay, we know the cosmic value is about 1 to 5 from cosmology of baryons to dark matter, roughly, right? But in galaxies, if you go far enough, for example, by lensing, or if you fit an NFW profiles and calculate the total required halo mass, you find that the baryons to dark matter is not 1 to 5, but maybe 1 to 100, 1 to 200. So what has happened? I mean, supposedly you start with if a galaxy just collapses, the ratio of, why should the ratio of baryons to dark matter diminish so much? So when dark matter people understood this and realized that this is the case, it wasn't so in the 90s. It's something that happened in the last 20 years or so. So they invoked something called feedback, namely, due to various processes, most of the baryons have been ejected from galaxies. Could be due to AGN activity, to supernovae, to so-called, I don't remember the exact term, but anyway, very violent and very unpredictable phenomena. So the whole process is quite unpredictable. So a galaxy that you see today has undergone very cataclysmic histories, shall we say, under which dark matter and baryons behave very differently. Dark matter is, of course, non-dissipative. This dissipation has a lot to do with the structure of galaxies. This is why they become disks, for example, by losing energy but not angular momentum. But dark matter does not dissipate. That is why it remains more or less spherical. They don't interact. Dark matter does not interact with radiation. Baryons do, and so on and so forth. So you can imagine that after this history, why should there be such a tight relation? Why should the baryons that, the little amount of baryons that remain there determine and dictate the full dynamics, when the full dynamics is really determined by the dark matter, by the putative dark matter. So that's a big issue. That's, if you ask me, okay, so people have come up with so-called challenges for dark matter. The co-cusp, too big to fail, things like this. To me, the real problem with dark matter is this, what I just mentioned before. How do you get such a tight relation between baryons and dark matter after you, in your picture, the history of galaxies is such that you would expect very wide variety, okay? Anyway, that's not what I meant to talk about, but yes. Right, so just very quickly to some of the predictions. So you remember, yes, so first of all, just to appreciate that this prediction of asymptotically flat rotation curve. So you see, well, you may say that these are not flat, but they are also not asymptotic yet. So what to do that astronomical limitations do not always allow us to go very far in a galaxy. We need the test particles, either stars or better yet, H1 gas. The gas doesn't go always far enough to give us enough sensitivity to measure rotation scale. But if you can go far enough, you see them flat. And as I said before, we now have very strong evidence from weak lensing, which is another way of probing the gravitational field, of these galaxies. In fact, what's important I'll come back to lensing later. In fact, I'll talk about it later. So let's just go on. So yeah, so rotation curves are asymptotically flat if we can measure them far enough. Remember this second relation between asymptotic speed and mass in baryons, of course. So it is this. There's no credit here, but this was done by Stacy McGraw at some point long ago. He sent me this curve, but the literature is now full of this. It is called baryonic Talley-Fisher relation. Okay, but so this is the m going like v to the power fourth relation. You can see that it goes very well through the data. And in fact, if you do scatter analysis, you find that the scatter is consistent with the errors, namely that it's consistent with zero intrinsic scatter. It's another way to present rotation curves. So what is plotted here is, okay, what I would call the mass discrepancy and how it depends on the acceleration. Because at some point I said that sort of the emblematic relation in MOND, where was it? There, here. So the emblematic relation in MOND says that the measured acceleration, well, let's look at this, which is equivalent mathematically. The measured acceleration should be a function of the Newtonically derived acceleration, the one derived from the baryonic mass distribution. And the asymptotic forms of this nu are determined by the basic axiom. So nu has to go to 1 for high argument and go to the 1 over square root of this for low argument. And so you can plot g over gn as a function of gn. Okay, to see if this is, to what extent there is indeed such a tight relation. This is what is done here. Again, this is from Stacy, as I said. Perhaps he has contributed more than anyone to testing MON and this. So this essentially is this function nu that appeared there, if you wish. So first of all, there is the fact that there is a tight relation, namely a nu is well defined, such a function is well defined. It has this asymptotic Newtonian regime at the value of 1. And this is 1 over square root of the argument. I should say, for example, that A naught appears here in 3 different roles. So one role is, as we already mentioned, is the transition from the Newtonian asymptote to the deep MOND asymptote. And here it appears in 2 different roles. So one role has to do with, because there are contributions here coming from very high acceleration galaxies, but going very far in radius. So asymptotically, you reach low accelerations. So many points here that come from the flat part of the rotation curves of high acceleration galaxies, but also many points that come from radii within galaxies that are everywhere in the deep MOND regime. Okay, so and A naught enters in different ways in them. This is a more modern version of the same relation. Now, okay, so what is plotted here is measured velocity over baryonic velocity squared, which is just g, which goes like v squared over v. So g over Newtonian g is a function of the Newtonian g. Here it's a somewhat different plot, but it's the same basically plot with much better data. I believe this is from the Spark. So in a sense, it is summarizing a lot of rotation curves, right? Basically, but as we know, summaries have a benefit of seeing the forest there, because when you look at this, a lot of trees, very nice trees, but you also want to see the forest somehow. So this is sort of the like a summary of rotation curve where you see that everything is behaving right. Okay, it's, I won't have time to, this is another very interesting relation. Surprising to me, I mean, not surprising, I mean, MOND sort of predicted it, but it was surprising to me that it could actually be measured again by so this is, the data is from Lely et al., also when he was in Stacy's group. And it has to do with, if you look at the disk galaxy, and measure its baryonic, just look at so-called central surface density. So you measure the surface density of the baryon in the disk. And you also somehow, I don't have time to enter into it, somehow determine the surface density in the halo of that galaxy, in the putative halo, of course. In MOND, there's no halo. The putative halo, which would be, in fact, the integral of the density along the axis. So it's the column density. You can indirectly measure it to within a factor of 2. And MOND predicts a tight relation between them, and this is what is observed. MOND predicts essentially this relation going through the data. Again, a note appears here in, it's a different type of data, I mean, that from the one that's here. I mean, the curves look the same in some sense, which is misleading. One can be misleading to think that we're dealing with basically the same data, but I mean, the same result, but they are not. It's a rotation curve. They come from far away. They have nothing to do. This refers only to the very center of the disk. It doesn't care about what happens there. Anyway. Okay, so now lensing. Lensing is very important, and it's a very recent result. So there have been a few in the past, but really the best data came out, and analysis came out a few years ago by a large group. The first author being Margot Brouwer. So they measured weak lensing. I will not repeat what it is. I'll only say that weak lensing allows you to go very far in radius. You see, this is measured in megaparsecs, so like up to 1 megaparsec. Rotation curves at best go to many tens of kiloparsecs, like 50, 60 in very good cases, but much less in many others. So A, you can go very far. B, you can analyze not just these galaxies, which are amenable to rotation curve analysis because they rotate, and rotation curve is rotation. So you need a rotating galaxy, so you need a disk galaxy. But lensing, of course, doesn't care about the nature of the central object, if it's rotating or not, or whatever. So it applies to elliptical galaxies as well as these galaxies. In fact, there was attempt to actually separate this. Maybe you don't see it. It says LTG, which are late type galaxies, which are basically these galaxies, and these are ETG, which are early type galaxies, which are elliptical galaxies. They are distinguished by their colors. Anyway, it's very impressive that so there was this data by Brouwer and also analysis, and they came to the conclusion that it agrees well with the predictions of MOND, going very far. But more recently, Mistele reanalyzed the data, I think, more carefully, shall we say. And they indeed find that the rotation curves, two within the error, two within uncertainties, remain flat very far. Hopefully, Stacy will have time to speak about this, or intends to speak about this also next talk, which is about another subject. It's about early galaxy formation, but I hope he will delve some more on this. Anyway, substantiated asymptotically flat rotation curve substantiated by weak lensing. Of course, the weak lensing has its limitation in that it's a statistical. You don't do it to individual galaxies, but anyway. Okay, then the second is the what I call the baryonic Talley-Fisher relation, the mass sigma relation. So you can of course determine the asymptotic speed. You divide your sample into several luminosity beams, which accounts for several baryonic mass beams, and you plot. So there are 4 points here corresponding to these 4 beams in the mass V flat relation. You see that they fall on the same relation that is gotten from galaxies. And I think this is also I replotted the data of Mistela et al. So that's why I call it adapted. And I think the line here is not the best fit. It's actually the MOND prediction. I'm quite sure. Okay, so you see. Right, and this is this relation. You see, this only goes as low in acceleration as 10 to the minus 2 of the value of A naught. So A naught is about this value. Goes only to about almost, but this is Newtonian. So of course, the MOND acceleration is predicted go like the square root of it. So it should go to 10 to the minus 1. With lensing, you can go much further. You see, instead of reaching only this point. So in fact, this is a reproduction of what you get from rotation curves, the curve I showed before. And look how much further the lensing data can go and test MOND. You can wonder why. So MOND predicts this curve, but only for isolated galaxies. So if the galaxy is subject to an external field, as I mentioned before, the so-called external field effect kicks in, and it makes the measured velocity want to go back down to the Newtonian regime. So anyway, I won't enter into this. Good. And then so all that I've said so far basically are mostly about rotating galaxies, these galaxies, except for the lensing, of course, which refers to this, but there are also independent analysis of pressure-supported systems, the dwarf spheroidal galaxies, elliptical galaxies, galaxy groups, galaxy clusters. I know that you usually suffer speakers to go rather beyond allotted time, but how much would you suffer?
Yeah, so our total session is 2 hours. So we're usually okay with speaker going up to 1.5 hours.
Good.
So another 20 minutes?
I'll try to be within at least this limit, and then what I don't talk about, I won't.
Yeah, you could take 20 more minutes. Yeah.
Okay, never mind. Right. So there are these systems that have been analyzed. I should say that galaxy rotation curves should really be considered the flagship of MOND testing, with all the aspects of them, the asymptotic flatness, the baryonic-Talley-Fisher relation, the rotation curves of low surface brightness galaxies, and so on. And because they are really the most amenable to the most trustable observations and the least susceptible to systematics. They do have the systematics, of course, but you can also analyze, of course, spheroidal systems, which are supported not by rotation, largely by random motions. Okay, so there are these systems. Very quickly, from analysis of the Andromeda satellites, internal dynamics, with some predictions. And so I won't show you how successful and discuss comparison with the data. So I'm only showing you this now that the time is so short, to show you that the tests have been done and they have been looked at. Okay, so these are there are 30 odd satellites of Andromeda, of the M31, nearest big galaxy neighbor of the Milky Way. These are concerned not their motion around Andromeda, which is also very interesting, but their internal dynamics. So you can measure the velocity dispersion in them by following individual stars, or not following them, by measuring well, you can also follow them now with Gaia. But anyway, measuring the the velocities of individual stars, determining velocity dispersion and comparing with estimated baryonic masses, and compare. Okay, so some of the points here are predictions. Okay, the circles are MOND predictions. In some cases, they're actually predictions in that they came before the measurements. Like in all these cases, they came before there was even a measurement. Okay, and in those cases, they came after simply because those were observed before. What can you do? Anyway, galaxy groups also subject to large systematics, because you can only measure line of sight velocities of galaxies in clusters, but if something is rotating in the plane of the sky, contributing to the centrifugal force, you cannot tell. You cannot know. I mean, in these galaxies, because you know the inclination, to correct for the plane of rotation. But here you cannot account for velocities in the plane of the sky. So there are large systematics. You expect large scatter, but still they follow the prediction of MOND. What is predicted here is log of the measured acceleration as determined from sigma squared divided by the size of the system. So typical velocity squared divided by size gives you acceleration, of course, measured acceleration, and divided by the Newtonian acceleration, which is calculated from mg over r squared, where m is the baryonic mass estimated from the luminosity of galaxies and so on. Again, there is systematics involved in group membership, making sure that you account for all the galaxies and so on. Never mind, but you can see that the thing has been looked at, follows straight line. Of course, this is the MOND prediction. Okay, galaxy cluster, of course, has been a pain in the side of MOND for many years. Why? Galaxy cluster do exhibit mass discrepancies right from the very center. But the accelerations as measured in the cores of clusters are not small in the sense of MOND. They are higher than the MOND acceleration. And so you would predict no discrepancies there, but yet there is a discrepancy. It was pointed out in the early 90s, in fact. And we should take this very seriously. I should say that, over the years, the 40 years that MOND has been around, there have been many challenges or sort of potential problems that have been pointed out. Here is a galaxy that seems to defy MOND. Here is another one that maybe defies it in the opposite sense. One has too much of a discrepancy, one has too little of a discrepancy, and so on and so forth. But I don't take those very seriously because, first of all, many of them prove to be, to go away, should we say, either because the data was misinterpreted, the systematics were not accounted for correctly, better data came in, and so on. Some even remain, but we have to understand that this is astronomy, and even if a perfect theory is expected to give wrong results for slightly wrong results for 20 in 100 cases, and strong this discrepancy in maybe 10 of 100, and anyway, we expect discrepancies, but in clusters the discrepancy is systematic in the sense that it's always the course of galaxy clusters show discrepancies that cannot be accounted for by MOND. And so this I do want to spend just a little time on. This is from an old comparison by not much has changed. I mean, from the late 1990s. Okay, so what he plotted was the dynamical Newtonian dynamical mass versus observed mass. You see that the discrepancy, this is, let's say, roughly within a kiloparsec of the center, roughly. So you see it's almost a factor of 10. Now, when you correct for MOND, so, okay, at 1 kiloparsec, the accelerations are already, maybe a few times below A naught. So you expect some correction by a factor of few. But when you correct for MOND, you still do not account for the full discrepancy. You are still left with a discrepancy of maybe a factor of 2. Okay, so that's has been with us for a long time. We don't have how should I say, a sure answer for it, but there are several possible answers. My own favorite is that we still have not discovered all the baryonic mass in clusters. Could easily be so. I don't have time to enter into what candidates there could be. But when Zwicky discovered the mass discrepancy in clusters, it was maybe 5 times or 10 times larger than it is as we know it now. It was maybe a factor of 50, not a factor of 10. But what happened in the meanwhile is that we discovered that most of the baryons in clusters are not in the form of stars, as Zwicky saw, but in the form of hot gas. Hot gas was discovered only much later with the advent of X-ray telescope and so on. So it could still be that there is still a fact, another. All we need to account for the mass discrepancy in cluster, let me just summarize in this way, is roughly as much matter as we do see in baryons in yet maybe undetected form. Could be called clouds, could be dead stars, I don't know. Okay, but that's a summary of it. And much has been made of the so-called bullet cluster in sort of proving the existence of dark matter. But in fact, if you accept this explanation for the mass discrepancy in MOND, namely that there is some additional amount of baryons, roughly a factor of 2, or roughly the same amount as what you see already, and you just let 2 such clusters collide, you will get the bullet cluster. So the same explanation accounts for the bullet cluster. Good. I will skip this. Okay, there is apart from discussing sort of equilibrium systems such as galaxies, cluster, and so on, MOND, of course, impinges a lot on time-dependent processes and like the formation of galaxies and their evolution and so on. And there have been quite a few works on this, especially in recent years. I won't have time to discuss them in detail. So the one, well, I prepared these slides before I knew that Stacy will be speaking just about this subject in the next talk. So it will save me one slide, but so one important question that concerns is how galaxies formed in the first place. They form differently in MOND and in the dark matter paradigm. So I won't discuss this further, but this question is very important, comparison and so on, especially with the advent of new results from JWST. Another very interesting issue has to do with what happens to open clusters when they move in the galaxy. Open clusters are relatively young, loosely bound clusters, unlike globular clusters, which are old and relatively more tightly bound. And when they move in the galaxy, they are affected by tidal forces of the. Okay, so let me before I come to this, because so I have this slide. This is the slide that Stacy is going to show you pictures from, so I won't say anything about it right now. Okay, yes, open clusters are rather loose, and when they move in the galaxy, they lose stars through what is analogous to the Roche-Lob transition point. There are 2 of them. They are tidal, shall I say, ridges. Okay, due to the tidal effect of the galaxy, the galaxy's field is not exactly constant at the position of the open cluster. It varies, and then there's so-called tidal effects, which stretches the effective potential due to the combined gravitational field and rotation. And it produces 2 points, one opposite, 2 points along the line connecting the, let's say, the center of the galaxy and the cluster itself, where stars are being lost little by little from the galaxy, from the from the open cluster. These stars that are being lost, they move relative to the cluster with very low velocities, so they stay near the cluster more or less, but not quite. So the ones that are ejected or that are lost towards the center of the galaxy form a leading arm, because the Keplerian angular speed at lower radii are somewhat higher. So things rotate with smaller periods around the galaxy at lower radii. So these stars sort of drip out of the open cluster, and they slowly, little by little, slowly they form a leading arm. Maybe there are some pictures here. Something like this. This is in fact from the data. So this is Hyades. No, this is Hyades, or some other clusters. And you see, this is the cluster, so the core of the cluster, and these are the so-called tidal tails. And the stars that are spewed from the other side, from the side opposite the galactic center, they lag behind a little bit. So they trail, and they form the trailing part of the tail. Okay, so now in Newtonian dynamics, these 2 points are symmetric. And so you expect the two sides of the tidal tail to be symmetric. So up to Poissonian statistics, they should contain the same number of stars, they should have the same length, more or less, and so on. In MOND, this is not so. MOND predicts an asymmetry in the sense that the leading arm should have more stars. For reasons I don't have time to go into, but I talked to Tejinder before my talk, and I recommended that they invite Pavel Krupa to talk about this subject, this very subject. So this will save me time. But
yeah, we'll do.
Yeah, so right. So I will just skip it and tell you that indeed, first of all, observations, we do see what is expected, and calculations in MOND also show that indeed this is what you expect. So these are the 2 subjects I was thinking of saying a little more about, but there are other things that I will only mention. So, for example, the disruption of susceptibility of dwarfs galaxies in galaxy clusters to disruption is different in MOND and in the dark matter paradigm, and you can use that to distinguish. And there is some interesting work by Elena Arsencio et al. On this. Of course, dynamical friction, for example, works very differently, because in the dark matter paradigm, you have all those particles around that constitute the dark matter, and they exert dynamical friction on bodies that move through them. In MOND, the story is very different. So phenomena that make use or depend or result from the presence of dynamical friction can be very different, and you can use this to distinguish. Another sort of evolutionary interesting process in our own backyard is the possibility that our Milky Way and Andromeda had a past encounter with some consequences, interesting consequences. So for example, and this again is different in MOND and in dark matter. Right, so you know what? I will not discuss theories at all. I meant to, but I will not because of lack of time. And I think it's the maybe less important aspect at this point. I just want to say some what I call epistemological comments. So the first is I already alluded to, is that what MOND tells you, or if you want to interpret MOND results and MOND successes in the framework of the dark matter paradigm, you have to say that the small amount of baryons that I should add remain there after most of the baryons were expelled by the processes that are invoked in the dark matter paradigm that you have to invoke in light of what we, the small amounts of baryon that we see. And yet they fully determine the dynamics, where in fact, in the framework of dark matter, it is the halo that determines the most salient properties of the dynamics, like the asymptotic form of the rotation curve, the amplitude of the rotation curve, the velocity dispersion in dark matter dominated systems such as dwarfs and so on. So keep this in mind when one comes to judge. Then there is the fact that A naught is determined from, you see, it appeared in many of the predictions of MOND, of course, and when you compare these predictions with observations, you, among other things, determine the value of A naught, right, which will give you, okay, so it has been determined in many independent ways, and of course, they all give consistent results. And this in itself should be telling us it must be something behind MOND. I mean, if it's dark matter, then, how do we get this A naught, and what is the meaning of A naught? There is no A naught in the context of dark matter, and why is it so ubiquitously appearing in different phenomena and so on? Just from history, this is taken from David Merritt's very good book on MOND that I was not aware of. This table that Perrin published in a book about the occurrence of what we call Avogadro number in many phenomena, many independent phenomena, and the fact that it has the same value. And of course, he saw this as evidence for the reality of molecules. I don't know if it was still disputed in 1916, but certainly it was disputed not much earlier than that. I mean, the reality of molecules. And the fact that there is this constant that appears in different phenomena with the same value is telling you something very important. And the other example is H bar in quantum mechanics. Also, I already mentioned those phenomena such as a black body, photoelectric effect, specific heat of solids, and so on, where there is this H bar and it's consistent effect. And this is taken from Planck's address, that is Nobel Prize lecture, and he said that after all these results, there is no other decision left for a critic who does not intend to resist the facts than to award to the quantum of action, which is his name for H, which has ever again yielded the same result, full citizenship in the system of universal. Right, so we have the value of A naught. As I said before, it has some connection with cosmology. It is the number itself, in the following sense that it is roughly of the order of the two acceleration constants that appear in cosmology. So one is simply the cosmological constant, that it defines an acceleration. I mean, if you think of the cosmological constant as the de Sitter radius, then c square over the de Sitter radius is an acceleration. And it turns out to be of the order of A naught. Also, another acceleration parameter is c divided by sort of the lifetime since the Big Bang, so, or c times the expansion rate, the present expansion rate of the universe. So c times H naught, right? C times H naught. And okay, we know that there is a coincidence between lambda and H naught that basically saying that lambda accounts for a reasonable fraction of the closure densities today. So it's the same coincidence. The fact that the two are roughly the same is not surprising, but okay, so A naught is roughly either this or this. If you want to use A naught to define some units like a length c square over A naught or a mass, you can define a mass or time. Of course, this length turns out to be the relevant cosmological scale. So you can ask, shall we take this seriously? Is it just a coincidence? I mean, historically, we know that people made much of coincidences that are probably not meaningful, such as maybe Dirac's large number hypothesis. I don't know if people still insist that it is meaningful, but anyway, it has in it the proton mass and things like this, which are probably not fundamental. But anyway, there are also counterexamples. One is, never mind, for example, it was realized, I mean, the speed of light was measured in phenomena that in the 19th century, phenomena that had nothing to do with light, just from electrostatics and so on. And we know that the speed of light appears, and people saw that numerically it roughly equaled what was known to be the speed of light then, but they didn't take it seriously. I suppose they've regretted it, but it was only Maxwell that later made use of this and realized that light must be an electromagnetic phenomenon. So anyway, I take it very seriously. Not the least of because there are reasonable explanations of why should cosmological scale enter dynamics within small systems. They are much smaller than the size of the universe. But okay, I think I will just leave you with this question. Not shall we take it seriously, but what could cause it? How could well, the two possibilities. So the same fact, the same thing enters both internal dynamics and cosmology. So there's one possibility, or there is some causal effect of cosmology on internal dynamics in galaxies, and the cosmological parameter enters effectively an effective theory for internal dynamics in galaxies in the form of this A naught. With A naught, A naught is it's an example I always like to give. If we measure phenomena on the surface of the Earth, and in high school we are taught that this little g of Galilei, 9.81 centimeter per second square, is maybe a fundamental constant, right? As long as we only do experiments on Earth. But then we learn that it is can be derived from, well, the mass of the Earth and the radius of the Earth, or if you want, from the let's say the escape speed from the Earth. And this little g is just the escape speed from the Earth divided by the radius of the Earth. Just like A naught is the speed of light divided by the radius of the universe. So, it's things like this happen. So, and there are quite a few potential frameworks, shall we say, for explaining this discrepancy. But this is a good point to stop. So thank you very much.
Yeah, thank you, Moti, for a great, memorable lecture. Now, as you have talked for quite a bit time, it's probably exhausting. I wanted to ask you, are you okay to take questions? Are you okay to take questions?
Yes, I will take questions.
So whenever you feel like stopping, just let me know, because otherwise I think this can go on for a long time now. I think there'll be quite a bit of discussion waiting. So I request the audience to please, I see there are a lot of comments in the chats, but instead of me going through that, kindly raise your hand if you want to ask a question. And so Subir, go ahead, please.
Thank you for a great talk, Modi. But to take up your last point, it is hard to see if, in the light of the coincidence you just highlighted, how A naught can be a fundamental quantity if it varies according to the present day Hubble parameter, which is neither fundamental nor a constant. Okay. Now, I know you mentioned something about the size of the universe, but there really is no correspondence between de Sitter space and any surface effect. There is a ADS-CFT correspondence. There is no DS-CFT correspondence. But that's sort of irrelevant. Right. The point I'm making simply is that lambda is required to be h naught square because that's the only parameter in the framework that you fit lambda to. Whereas a naught, you're fitting to a completely different set of data, as you say, and it's just very hard to see how the two can be related. I wonder if you have.
Okay, yes, of course. So first of all, let me distinguish. We said a naught could be either identified with h naught, with c times h naught, and of course h naught is not constant. I mean, if it's the if a naught is to be identified with c times the expansion rate of the universe, then of course it must have been very different in the past, much larger. Okay, so that's one possibility to be tested, because you can, in principle, look at galaxies or measure rotation curves of galaxies at high redshift. I know there is a plan afoot to do this, actually. And then you can measure a naught from, let's say, the Talley-Fisher relation as applied to high Z galaxies and see if a naught indeed is a constant or varies. But if you identify it with lambda, then it should be a constant. I'm not saying a fundamental constant. I'm, totally happy to think of a naught as an effective constant, just like g on the surface of little g on the surface of the Earth is just valid, the surface of the Earth. But
that is precisely my point. Lambda does not go as h square. It has to be h naught square. Because if lambda went as h square, then you could just transpose it to the left-hand side of the Friedmann equation.
No, then I don't see what you mean. I'm sorry.
Well, I'm saying that lambda cannot be...
Which lambda?
The cosmological constant is not cannot vary with time. It is h naught square. It is not.
No, but I don't want it to vary with time. Why should it vary with time?
Oh, in that case, okay. So in that case, your a naught happens to be related to the value of lambda as inferred from data, which goes as h. I understand what you're saying. Well, I don't.
Subir, it might interest you. Let me show you one of sort of, let's just call it a possible framework for explanation, okay?
Okay.
So let's say we live in a de Sitter, almost de Sitter space, right?
Yes.
Now, there is such a thing. Okay, what I noticed is the following, that, okay, there is well, it was my idea at some point that maybe inertia, so in MOND you need to define your acceleration with your absolute acceleration. So where is the frame that will provide this? So I thought maybe it's the vacuum, okay, the quantum vacuum. Now you can measure your absolute acceleration with respect to the vacuum, yes, using the Unruh effect.
Yes.
Right. So I said to myself, okay, Unruh effect for at least for a body moving with constant speed says that the temperature. So this observer finds itself immersed in a black body with a temperature that's proportional to the acceleration.
Yes.
Okay, so maybe inertia has something to do with this, that it's like a back reaction of the vacuum that resists acceleration and tries to bring this Unruh temperature down to zero, sort of like in the Le Chatelier principle. Okay, so basically you say, so let's say inertia is proportional to the Unruh temperature. That's the basic relation. So now I ask myself, okay, but what happens in the framework of a de Sitter space? So in de Sitter, we know there's something called the Gibbons-Hawking radiation, which is analogous to Unruh, and in which even an inertial observer finds itself immersed in black body, which is related now to the cosmological constant.
I see.
Okay, so now I ask myself, okay, so what does an accelerated observer sees when it is in a de Sitter?
Yes.
So the problem was solved for me, and it turns out that he sees himself embedded in a temperature that knows both about the acceleration and about this A lambda. A lambda is just C square over lambda, okay? Over, over the de Sitter length. And it behaves like this. So I said, okay, let's say inertia is just proportional to the difference between the temperature the observer sees and the minimum temperature that he can reach just by being inertial, which is just T lambda itself. Okay, so you write something like this, F equals m times T, and it turns out to give exactly a behavior like MOND, namely for high acceleration. I mean, when A is much larger than then A lambda, it goes to A. When A is much smaller than A lambda, it goes to A square over A lambda.
Okay.
Okay, so it's just, it's a caricature of something.
That's interesting. Yes, I see.
But at any rate, it shows that there's no matter of principle issue here, that there might be some frameworks in which this can actually happen. It is still an open, very intriguing question.
Yeah,
Certainly
Moti,
very
I wanted to, sorry for interjecting. Both you and Subir have raised a very interesting situation related to De Sitter, and I wanted to make a few remarks on that based on our recent work. So
Okay.
we agree that MOND has a scale invariance, and so does De Sitter, whereas general relativity does not have it. So I now try to explain that for me, MOND is that part of a symmetric, that part of a gravity theory which was there on De Sitter before we made the De Sitter to GR transition. MOND is that part of the gravity theory which is still the unbroken symmetry. It's like carrying a memory of De Sitter. So I want to make an analogy with electroweak theory which we used in our work. So when the electroweak symmetry is broken, the electrodynamics part, as we know, is the unbroken symmetry. So for me, MOND is the unbroken symmetry, GR is the broken symmetry, and before the De Sitter to ordinary universe transition is made, the theory of gravity is not general relativity. It's something like general relativity, direct product, relativistic MOND, precisely in analogy with electroweak. The weak force goes with general relativity, and electrodynamics goes with MOND. So that's why MOND preserves the scale invariance memory of De Sitter. So what the question that I would have had is, what do you think about this? And if I ask for a relativistic scale invariant theory, what all choices do I have actually? We just take the MOND principle of scale invariance and demand that theory become relativistic. Where would that lead us?
Well, I mean, there are relativistic versions, I mean, extensions of MOND.
Right.
Right?
But that's not unique, is it?
No, of course not. I mean, even the non-relativistic, there are several non-relativistic theories that we already have. Who knows how many more there are. And in fact,
Yeah, so
if you ask me, none
I
of
don't
these.
want So I was saying I don't want to think of MON as a relativistic theory of gravity or a modified gravity, just as electrodynamics is not a modified weak force. Rather, I want to think of MON as a fifth force which starts to dominate over general relativity at low accelerations, just as the electrodynamics dominates over the weak, let's say, over some energy scale. So, in that sense, I would like to think that there is a unique relativistic
Okay,
fifth force relativistic theory, which is left over from the De Sitter phase.
okay. I mean, I cannot really comment as what you said somewhat goes above my head, I should say. But okay, I mean,
Yeah,
uh,
maybe I don't know if someone in the audience wants to comment, or we can go to the next. So I think MOND is beautiful. It is a phase between De Sitter and GR. Normally, we think GR goes over to, on the cosmic horizon, it just goes over to De Sitter, but I think that's not true. There are three phases: the De Sitter phase, the MOND phase, and the GR phase. So Indranil is saying something. What's Indranil saying? You cannot simply treat MOND as an extra force, since then you would have G equals G Newton plus square something something. No, where one dominates over the other. In the deep MOND regime, MOND dominates over Newton. I don't want to add them like this. In the interpolating region, I don't know what's happening on. I mean, in the deep MOND and the deep Newtonian regime, you have either one of them. Interpolation, I don't know.
Incidentally, maybe it's important point in connection with relativistic MOND theories. Okay, so this is something I meant to talk about. Maybe it's a good opportunity. You see, take this coincidence as you wish, but the fact that A naught is of the order of C square of some scale of the universe means that you cannot have a very relativistic system that is smaller than the universe. If you want to have, let's say, a black hole such that near the surface, the acceleration is of the order of smaller than A naught, then you see that the Schwarzschild radius has to be of the order of the de Sitter radius. So
Yes,
in
this
fact,
agrees with what I'm saying. This goes with what I'm saying, that there is a deep MOND regime in between the horizon and the GR dominated region. That's what you are saying, yeah?
yeah, I'm saying that basically that the only strongly relativistic problem that you need to treat in MOND is the universe at large, because all black holes, let's say, all systems that are very, highly relativistic are much above the MOND acceleration. So they would be general relativistic,
I
essentially.
agree. I agree. I agree. Yes. Yes.
Can we just take one or two more questions?
Yeah. I think
That will not require answers. I'm getting.
I agree. It's been long. We are almost at the end of 2 hours. Fortunately there are no raised
And
hands.
I'd be happy to, if people want to send me some questions by email, I'll be very glad to try.
Yeah, there were a lot of comments in the chat. I request the commenters to please get in touch with Moti directly. So, Michael, you want to say something?
Yes, thank you very much, Tejinder. Thanks very much to Moti for a very, very wide-ranging and deep and beautifully presented talk. I was just wondering if you had time to respond to George Sparling's question in the chat about Minkowski. It struck me as a particularly intriguing.
What was it? Because I don't. Let me see.
Okay, hang on, just let me
I look at the chat.
What he's saying is that MOND is based on a Newtonian view of space-time. Now we know that should go over to the Minkowski view of space-time. So what does MOND do there? My understanding is probably ask for a relativistic description of the acceleration.
Yeah, but okay, so there is a long list of relativistic extensions of MOND. Okay, so they automatically take care of what you worry about, in the sense that of course, they live in space-time. They have, or they coordinate invariances and so on. Sure. But in each of them, the acceleration that eventually becomes the acceleration relevant for MOND in the non-relativistic regime has a slightly different meaning, somewhat different meaning. For example, in Bekenstein's first really full-fledged relativistic theory, it extends, generalizes general relativity by adding a vector and a scalar gravitational degrees of freedom. Okay, and the gradient of the potential of the scalar is what becomes, in the non-relativistic limit, becomes the gradient of the Newtonian potential. For example, in some other theories, I have my own bimetric theory, in which the two metrics that serve as gravitational degrees of freedom, and somehow we know that a metric does not define an acceleration. You cannot define covariant. You cannot define a covariant acceleration in MOND, in relativity, but because, for example, the connection, the Christoffel symbol, the connection which would serve as acceleration is, of course, not a vector, not a tensor. But if you have two metrics, you can take the difference, and this defines an acceleration tensor. And in the limit, the non-relativistic limit, it becomes a gradient of phi and so on. So yeah, there's no issue, I think, with this.
Yeah, one point that I found very interesting, Moti, is that when you write MOND as a modified gravity, the acceleration is proportional to square root of mass.
Yes.
So what we tried to do is build a theory like electrodynamics, where there is a gauge field with a vector potential, which instead of coupling to electric charge, couples to square root of mass. We make a relativistic theory like electrodynamics, which couples to square root of the baryon mass. And we found that it actually works quite well, which is what I sent to you, and you said whatever, it was fuzzy. But I think
I didn't say it was fuzzy. I said it was, as I said before, it went above my head. I mean,
yeah, but
that was my expression.
I think you are being modest. Yeah. So
No, really. I mean, we come from different backgrounds after all, and perhaps if I invested a lot of time in it, I could understand it. But that's the truth. I mean, there's much to do, and
Yeah. Okay, great.
Moti, could I ask a sociological question, please?
Yes.
You're about to go. Well, when your theory is now 42 years old, and you've obviously faced quite a lot of, had a lot of support as well as criticism over all these decades.
Right.
And please don't mind my asking this, but on the whole, would you say that the scientific community has responded appropriately if you even out the sort of extremes here and there? On the whole, do you think that
Yes,
there is still a climate, as we would like to see, of open-mindedness towards new ideas?
yes, I think so. So let me put it this. First of all, we get a lot of odd ideas that are put on the table, right? In
Yes.
physics. So I think the fact that the community, that there is this resistance is quite healthy, because let's say, only one in in 1,000 such theories are actually. So this is good. I never complained about the resistance.
Yes.
There is there is a lot of openness. Now, it has to be understood. I mean, it's not like quantum mechanics, where there was no competing theory that could explain the same phenomena.
Yes.
There is dark matter. There is a lot of vested interest. There's people have invested a lot in the theory, and I understand that the resistance is natural. It's not that I always agree with how people react and behave and say, but yeah, on the whole, I'm maybe not complaining at all. I mean,
But Moti, I'm sorry, I disagree with you. I'm very disappointed with the dark matter community's response to the development of MON, in particular astronomical observations also. Like in recent years, the gravitational wide binaries, they don't even talk about it. And similarly with early web galaxies, It's like trying to,
But
okay, that got some attention.
Tejinder, first of all, I think that what you call dark matter community, they don't say everything, they don't say all they think. Down deep in their heart, you can see indications of this, that many of them do take MOND more seriously. They do think about it. They do try to work out things. But look, what can they do? I mean, if they admit that MOND is correct, then most of them, I don't see them do something else. I mean, so it's in some sense survival as scientists that dictate that they behave in this way. Maybe I'm more forgiving, but
Yeah, I've seen you all these years. You are extremely kind. You never get annoyed. You never get angry. But I think the situation has not been fair. I will be very open about it.
no, it's,
Both,
But
I mean,
Tejinder,
yeah. I mean,
absolutely, I think we should all admire Moti's patience and perseverance. This
look,
is very, very, how shall I put it? You're setting an extremely good example for us all.
yeah.
if we all went by the rules of science, namely all that matters is the truth, then yes, they're misbehaving. But I also take into account the constraints that people have on, what they can.
Yeah, but what I'd love, the part that is sad is that this greatly slows down the progress of science. In
Yes,
all this progress of, I mean, I would say that about string theory also. They slow down the progress of science. Okay, and now that we know that the theory has problems, please admit that the theory has problems so that we can collectively move on. So to me, this is somewhat like the geocentric hypothesis story.
yes.
We are in a situation like that. You are somewhat like heliocentric versus geocentric, in my
No, it
opinion.
is true. It is more similar to this because in this case of Ptolemean versus Copernican, there was indeed a competing and very old and entrenched theory that claimed to explain the same phenomena. So it was much harder than in the case of quantum mechanics, for example. But
Yes, true. Yeah. So my last question would be, what do you think would be an experimental discovery which would, let's say, close the case for dark matter and make it very solid for MOND? I mean, do you have something in
you mean
mind?
observational or experimental is hard to think
Either
about.
experiment slash observation.
Because with experiment, people have suggested things like, but it's difficult because, as I said, for example, if you want to go in the solar system, there is a point where gravity, let's say, of the Earth and Sun or all the planets or whatever balance and where accelerations are zero. And around this, you could, in principle, go and measure things. Okay, but as I said in the beginning, the MOND does not make primary predictions about this because it depends whether it's modified inertia or modified gravity. So about experiments, and people suggested in the past, when the LISA Pathfinder, part of the proposal of LISA Pathfinder was to, once it is done with its mission, with its primary mission, that to send it to the point between Earth and the Sun where gravity vanishes and try to measure something. Okay, so, but it's very difficult. Now, observationally, so we're dealing with astronomy.
Right.
As far as I'm concerned, that there already have been quite decisive results. I mean, the results that I show, in my opinion, are decisive. Now, we will hear from Stacy, for example, about formation of early formation of galaxies that MOND predicted. Was Bob Sanders that dealt with this in the 90s, predicted. And what we observe with JWST is very much unlike what has been predicted. It has been predicted. I mean, you cannot now come and predicted something completely different from what has been observed. So, okay, so now, dark matter is so flexible. That's a problem, that it doesn't, it doesn't make, I mean, if you take dark matter to mean anything, then it doesn't make any predictions. If you take it to mean specific versions like cold dark matter or WIMP or whatever, then it does make predictions sometimes, but those predictions fail. So what they do is go back and change there's so much you can play with anyway that
a laboratory test of MOND is, I guess, impossible, no? To create a laboratory test of the law of gravitation, say at very low accelerations.
People even suggested this. There was a long Nature paper long ago suggesting, once every or twice a year, the acceleration due to the rotation of the Earth cancels the acceleration due to the Earth going around the Sun. But this happens it happens near the North Pole for about a millisecond in a volume of about a millimeter or something like this. So you have to go there and measure. No, it's difficult. It's very difficult.
Okay, great.
But Gedanken experiments you can do it. It's been dwelt on, for many times. People, of course, it's one of the first things that people think about.
Where I made peace with dark matter people is to say that underlying MOND, there will be a fundamental field, say a gauge field. It'll have a gauge boson, it will be a new particle. That is dark matter. It has Mondian character, but it's a new particle. And in that sense, it's dark matter. But they are looking for it in the wrong place. It means maybe not a WIMP or massive particle. Maybe the dark matter is massless.
No, but there is a big difference between having a new particle that, okay, the new particle can do one of two things. It can enhance gravity and account for the anomalies by enhancing gravity, by just being there, by providing gravity by its own weight, by its own energy density, okay?
Right.
So that is what I call dark matter. But it can also mediate a new kind of interaction. So that is not dark matter to me. If you had a particle, if you had a field that all it does is mediate a new interaction that accounts for MOND, this is not dark matter. It doesn't act like dark matter.
Okay, that's a good point. I had not looked at it. So
you should not call it dark matter, because people say, anyway, you had new fields, so it's like dark matter. No, it's not.
Okay.
So one difference is that in a MOND frame, if you only change the interaction, that still the baryons determine everything. But if you have really dark matter in the standard sense, then you are not.
You are right. I agree. What I have in mind is a new interaction amongst baryons, apart from the ones known to us.
Fine. But all relativistic theories, or not all, most of the relativistic MOND theories do this. They add fields. They add, in Teves you have a scalar and vector field. There is Einstein ether theories. There was recently theories by Skordis et al. They all had gravitational degrees of freedom that, they change the gravitational interaction between baryons.
Right. So I think but your viewpoint then is that dark matter is fermionic. Is that what you're saying?
No.
Not necessarily.
No, I mean axions, there's axion dark matter.
Yeah. Okay. I see. Yes. Great. Thank you.
Thanks again. Bye.
Okay. Bye, everyone.
Yeah. Okay, great. So I'll close.
Thanks once again.
Okay.
Yes. Yeah. Right.
Thanks once again, Professor Milgrom. Thank you.
And thank you all. Thank you very much.
Wonderful talk. Thank you very much indeed.
Bye.
Okay. So in 2 weeks' time, we welcome Stacey McGough.
Right. I'll be there. I'll be there.
We'll want to see you for that as well. Great. Very good.
Bye.
Take care. See you then. All the best.
Bye, everyone. I close the meeting.
Cheerio, Tejinder. See you in 2 weeks.